Hello, this is Mr. Stansbury. I'm going to take you through the notes on growth and decay. At the end of this, you should be able to say, I can use exponential growth and decay models to solve real-world problems. Okay, so first thing, for exponential growth and decay models, we're going to make up a population model and use that for our example here. So here's one, population of at n, so that's time, that's the n is the time, equals 200 times 1.05 to the n, versus population at time n equals 200 to the 0.95 to the n power. Okay, so P of n is population after n weeks, so instead of years, weeks. N is the number of weeks since original population was measured. For both, 200 is the original population. So this is the original population is this, because if you put in 1 for n for the number of weeks, this turns into 1, and 1 times 200 will give you 2. Same for both of those. Okay. The first equation is 1.05 means the population is growing by 5%, because what you always want to do to figure out your growth or decay rate is you take 1.05 and you subtract the original 1.00, because this is the original, that's the original 100%. Okay, so this means that this is growing by 5% growth. Okay, so this one here growing by 5%. This one here, we do the same thing. We take 0.95 and we subtract our 1, our original 100%, and we get negative 0.05, which means that's negative 5%. That means it's called decay. It's decreasing by 5% each week, where this is increasing by 5% each week. Okay, so let's look at an example and put this into practice here. So Penelope has been tracking a population of emperor tamarin near her home. The population is given by P equals 42 times 1.06 to the n, where n is the number of years after the first population was recorded. Find the original population. So original population is when n equals 0, right? So if we do 42, we could even do our whole equation here. Oops. Population equals 42, 1.06, and n is 0, so that's to the 0 power. So that turns into 1. So that means our original population is simply 42. Okay? Find the population after 5 years. So now if we're going to do that, so this was A. If we're going to do that for B here, that's when n equals 5, right? So P equals 42, 1.06 to the 5th power. So that's where we're going to want to use our graphing calculator. And we can do 42, and we can even make it look just like it looks here. Parentheses 1.06 to the 5th power. Hit equals, and we are up at about 56. It is about 56 tamarins, right? Emperor tamarins. Okay. Draw a graph of the population over time. So, nice part about this is we actually just created a couple of points, right? We know that when time is 0, we know that we're at 42. So let's maybe do these by tens. Okay, so we did this by tens, and we'll do this time in years by just singles, hoping that it'll work. So we get n equals 0, and then let's do this in a different color. So we've got our population was 42. So here's our y-intercept, right? At 42, our initial population. And then at 5, we're now up at 56. Right, so right about there. Okay, draw a graph of the population over time. Okay, so now this is an exponential, so we're going to probably want to come up with a few more points in here to see what's really going on. So let's maybe plug in, say 2 here. Change my color back here. So C, let's just try some more. Let's say if n equaled 2. We get P equals 42 times 1.06 to the 2nd. And what we can do here is a little, I don't want to say trick, but you go back and highlight that, push enter, and you should be able to now edit that. So now I'm going to turn that into a 2. Push enter, we're at 47. So 2 is at about 47. Right about there. And then let's maybe try 10 also. Let's see what happens when we get out to 10. N equals 10. We get P equals 42 times 1.06 to the 10th power. Right? So I'm going to go up and highlight that. Push enter. And turn that 2 into a 10. Equals 75.2. Okay, so that gave us 75.2. Oops, let's see, equals 75.2, and the other one was 47.2. Okay, so at 10, we're at 75.2. So it looks like it's curving up a little bit here, right? Because it is growing exponentially over time. So, you know, you would, if it continues to grow like this, like at, say, if we had 100 years, it's going to be significantly bigger. Okay, so we have done those 3 things. Draw a graph of population over time. Estimate how long it will take for the population to reach 100. So, estimate means, you know, just kind of give it a good old guess. I'm gonna help remind you of something that you used to do in Algebra 2 with good old logarithms, which is coming up here pretty quick in our curriculum anyway. So we want to know when the population is 100. So let's do this. So for part D, we're going to do 100. When does 100 equal 42, 1.06 to what power, right? To our n power. So we want to know when that's going to equal 100. Now, we can use logarithms, and we can actually also use the graphing calculator as well. But I'm just going to show you this here. So to get n by itself, the first thing we got to do is divide both sides by 42. So we got 100, not 10, but 100 divided by 42. And that gives us 2.381 equals 1.06 to the n power. Now, whenever your variable is the exponent, what you want to do is just do good old logarithms. And now the long way is we do log of both sides and we move stuff around, figure out what it is. Here's what I'm going to do. I'm going to take you straight to the shortcut. Log 2.381. Well, let's just do this. Log 1.06 to the n, right? And then once you have done the logarithm of both sides, this n can come out front here. So this really is n log 1.06. And this is still log 2.381. So then really to figure out what n is, we divide both sides by log 1.06. Okay, that wasn't the shortcut. That's actually the long way, but you know what? This way is really nice because you can make this make sense. Okay, the only thing you have to remember is when you do log of both sides, this variable, this exponent can come out front, and it's n times log. Okay, so then really all we need to do is take the log of this, and I would highly suggest using this non-rounded number right here. So I'm going to do log, and I do second answer equals, that's what the log of 2.381 is, and then I'm going to divide by log of 1.06. And that gives me that it's going to take about 15 years, 14.9 years. So n equals about 14.9 years. Okay? Okay, I've got one exponential decay problem for you, but before we do that, let's take a little comedy break.
And you wonder why women mature faster than boys. While we playing with make-believe stuff like Ninja Turtles, you learn how to take care of babies. and cooking little brownies with light bulbs and stuff is stupid. Don't act like you ain't had that easy bake ridiculousness. It takes 6 weeks to make a brownie in that silly thing. It was a good brownie though. It wasn't done in the middle. It was a good brownie.
All right. Example 6. Cup of fermented yak butter tea is left out on a table. The tea cools down as given by the formula T equals 100 times 0.72 to the M plus 70, where T is the temperature in degrees and M is the time in minutes. Okay, find T when M equals 0, 1, and 2. Okay, so if we plug 0 in, since we're going to plug in several, let's do this. I'm going to show you. You can certainly do this by hand, but you can also do this in the graph here. So I'm going to clear out everything else that's in here. Oops, I'm going to try to anyway. There we go. So I'm going to do this. I'm just going to put this in just like it looks. 100 parentheses 0.72 to the, and now this is M. Any variable you ever use is always going to be this here. That's going to be to the X, and then plus 70. Okay, so now you can graph it, which isn't going to do us a whole lot of good, but then what we can actually do is we can do second graph, which gives us a table. Okay, and then it's going to give us it's going to give us all the answers. So like at -3, which wouldn't make any sense because that's time, right? So we wouldn't go to negative time. But look here, at 0, this thing says that it's 80 degrees. That sounds a little fishy. Let's see, what did I do? Oh, because I put in 10, it should be 100. Second insert. I say that does not sound right because it should be, oops, I still have it backwards. Let's do this 1, and then that's a 0. The struggle is real. There we go. Second table. There we go. Now that makes sense. 0 at time 0, we're at 170 degrees, right? Because this turns into 1, so we have 100 plus 70 is 170 degrees. So we can even make ourselves a little chart here. The temperature, and then this is the minutes, right? 0, 1, and 2. So at 0, it's 170. At 1, we're at 142 degrees. So after a minute, it's cooled down to 142 degrees. And then after 2 minutes, it's cooled down to 122, let's call it. 122 degrees. Okay, plot the graph of T for 0 is greater. So M is greater than or equal to 0. So we're going to plot the graph here. So time in minutes. So we can probably just do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? And then temperature, we'll want this thing to go up to at least 170. So let's maybe go 200. And then we'll go, basically these are all by, oops, that's wrong. These will all be 20s, right? So this will be 20, and then that'll be 40, 60, 80, 100, and 120, and 160, 200. Okay? So, at 0, we are at 170, which will be right here, right? Let's do that in a different color again. So at 0, we are at 170, because that's 180 up there. At 1, we're at 142. And at 2, we're at 122. Right? Okay. Now, hopefully you can look at this thing here and say, look, there's our asymptote at 70. So we know that this thing will never get below 70. So there's our nice little asymptote right there. And this thing is going to come down here and kind of get closer and closer and closer to this value here, but never actually hit it, right? So let's see, we can kind of graph this. It's kind of coming down, and then it's going to kind of flatten out like so. That's a sketch of our graph. Okay, how long until the T reaches 76 degrees? So we could use our graph to kind of estimate, or we can plug it in again as well. Or, let's see, another way we can do this here is just scroll down on our table until we get down to 76 for our Y value, right? Okay, so looks like it's around 8.5 minutes or so. It's between 8 and 9 minutes. So 8.5 minutes about, right? Now, you could actually plug it in. Oops, sorry, this is for C. We could plug 76 in for here, divide both sides by 100. Oh, well, actually, sorry, add 70 first, then divide by 100. We could do all that. This here gives us a pretty close estimation, so we can go with that. And then also, yeah, that's probably going to be our easiest bet there, especially since we're running so long on time here. How long until the T reaches 65 degrees? Well, since our asymptote's at 70, never. It'll never get below 70 degrees because that would be like the room temperature. Okay? All right, sorry for the longer video here, but I wanted to give you an example of both growth and decay. If you have any further questions, please feel free to ask. Thanks.